Real-world task inference using visual bag of features and eye movement data. The system we developed is implemented as follows. A two-pass approach is used, combining both visual bag of features and eye movement features. The first pass goes through the videos of the task at hand, extracting 100 by 100 pixel patches from the fixation points of our participants. The second pass goes through and extracts a feature vector that is representative of the participant's eye movements. For instance, the mean duration of fixations and the mean of saccade magnitudes. We then train a support vector machine, with 65% of our extracted data being used for training and the remaining 35% being used for testing. We then can compare both bag of features and eye movement features individually as well as together to assess which produces the best results. In this study, we conducted one experiment which consisted of participants performing 6 different tasks while wearing a head-mounted eye tracker. We had 12 subjects in total, 9 of which were males and 3 were females. The participants were split into 2 groups of 6, which performed their tasks at 2 separate locations so as to account for varying backgrounds. For the tasks themselves, participants were asked to count 5 chairs, have a conversation, make coffee, walk down a corridor, wash their hands, and write their name. All of these tasks, along with their accompanying fixations, will now be demonstrated. Counting chairs. The participants were asked to count chairs in no particular order. Having a conversation. Making coffee. Note that participants were not instructed on the order in which they were to perform the task. Walking down a corridor. Note that participants were only given a start and end destination. Washing hands. Note that participants were not instructed on the order in which to perform the task. Writing your name on a chalkboard. Here are a few sample patches that were extracted from participant videos. Notice how washing hands, writing name, and making coffee all include hands in the patches. Here we can see 2 extracted scan paths from participants. Notice that the paths are for the 2 tasks of washing hands and making coffee. Using purely a bag of features approach, these 2 were misclassified, but it is clear from these images that the eye movements required for both activities are very different and can be used for correct classification. For evaluation purposes, we used both confusion matrices and binary classification tests as defined here. Here is the confusion matrix for our tests in regards to bag of features. The diagonals show the correct classification for each task. Take note that the count of patches that were correctly classified is always the highest for each specific task. Notice how making coffee and washing hands have such a low percentage of classification. We attribute this to the fact that the patches extracted from both these tasks include a lot of hands, causing misclassification between the 2 tasks. Here we can see the bag of features binary classification. Notice again that washing hands and making coffee had the lowest accuracy, which as a consequence brought the overall balance accuracy to 78.14 for this technique. Here is the confusion matrix from our test in regards to eye movement features. The diagonals show the correct classification for each task. Take note again that the count of patches that were correctly classified is always the highest for each specific task. Here the percentages of correctly classifying washing hands and writing name are very low compared to the others. We attribute this to the magnitude of the saccades involved in these tasks, since both require very slow, steady, fairly centralized eye movements. Here we can see the eye feature binary classification. Again, the washing hands and writing names tasks had the lowest accuracy due to eye movement patterns that were similar between them, which, as a result, brought the overall balance accuracy down to 79.25%. Here is the confusion matrix from our test in regards to the combination of both bag of features and eye features. Notice that using the technique that we developed, we were able to raise the accuracy of correctly classifying washing hands to 70% from 39% and making coffee to 87% from 48%. Here we see the binary classification for the combination of bag of features and eye features. This raised the overall balance accuracy to 92.25% as opposed to the 78 and 79% accuracies we were getting with each technique individually. As you can see, the results of our technique are very promising, and we hope in the future to extend our model to infer subtasks that are being performed by a viewer while they perform a bigger, complex task. We would also like to explore the opportunity to have the system work in real time. A real-time task inference system will help in both learning and education, as well as help researchers understand attention switching between tasks, which we feel confident that our technique can achieve.